Hi OpenXML developers, this is Eric White with OpenXMLDeveloper.org. I recently released a new module in PowerTools for OpenXML. This new module enables you to search and replace content in Word Processing ML and Presentation ML using regular expressions. You can search for content with a regular expression, and optionally you can replace the matched content with a specified string. In the previous screencast, which you can find at this link, I walked through the operation of that class and talked about some of the interesting semantics of how we need to introduce revision tracking if revision tracking already exists in the document, and if the content that we're finding and replacing is either partially or in inserted content. Behavior differs based on whether the new author is different from the previous author of that tracked revision. I recommend that you watch that screencast before watching this screencast. Today I'm going to walk through some of the code. I'm going to explain the algorithm. This will be useful to anyone who's porting this code to a different language. It also will be useful to me in the future when I need to come back and make revisions to this code. So let's dive in and get started. Here I have the zip file for OpenXML PowerTools 2.7.04. First I'll unzip it, extract everything. Because I've downloaded this from the powertools.codeplex.com site, I need to unblock all of these files. That will make it easier to work with. I won't get the various warnings from Windows that I'm working with downloaded files. So after unzipping everything, I type PowerShell right there, and that opens up a PowerShell command prompt for me at that location. I'll enter the command dir-recurse, pipe that into unblock file, and we're done, and we can exit. Now I'll drag and drop this solution onto Visual Studio 2013. 2012 will work just as well. You can build this with 2010. You just have to put together the project yourself. The PowerTools don't use any feature that is not available in 2010. This example here, OpenXmlRegex 01, exercises the OpenXmlRegex class in a variety of ways. I'll press Ctrl F5 and make sure that the project can build and it can run the example. And everything looks just fine. In the previous screencast, you saw the behavior of that example in depth. Let's now go into the OpenXmlRegex module, and I want to explain a few things about how this works, some of the more interesting characteristics of this class. The first thing that you'll notice is that all of these various methods, whether they are matching content or replacing content, all call this internal method replaceInternal. There's a lot of code that is in common between all of those methods, so it made good sense to put all of that code into one method and then call that method from the various other methods. Here's the replaceInternal method. Because its semantics encompass both matching and replacing text, it needs to accommodate that. And if you pass in null for this string replacement argument, then it will just do matching or searching. For the callback, if you pass in null for that callback, it is just as though you had a lambda expression that returned true. It will do all replacements. If you pass in false for this track revisions argument, then of course it won't introduce tracked revisions into the markup. It'll still process content that happens to be in tracked revisions, but it won't introduce new tracked revisions. The new markup that is inserted won't have revision tracking markup. And if you do pass in true for this track revisions argument, then you need to pass in a revision tracking author. All tracked revisions are required to have an author attribute on them, so this is how we specify the contents of that author attribute. And as I mentioned, it also has impact on the actual behavior of this class. If you watched the previous screencast, you saw how the way that you use this class is that you query for any number of paragraphs. You then get an IEnumerable of X element for your paragraphs, and you pass in that collection into the various methods, and then that gets passed to replace internal. Right here you can see where the code looks to see if the namespace of the first paragraph is in the word namespace, then it will execute the following code. And if we drop down here, we can see if the first element in that collection is in the presentation ML namespace or in the drawing ML namespace, then it executes the code down here. Next point about this code is you pass in your collection of paragraphs, and this code is going to alter the contents of those paragraphs. It's going to leave the paragraph elements themselves alone. You're passing paragraph elements from the XML tree of your main document part or from a particular slide or what have you. It's the contents of those paragraph elements that get mutated by this method. What we can see here is the code iterates through every element in the content collection that you pass in, and it calls this WML search and replace transform for every paragraph in that collection. This method, WML search and replace transform, is a recursive method, so it deals with all of the various interesting aspects, like if a paragraph also contains a text box and there's content in those text boxes that need to be replaced based on the regular expression that you pass into these various methods. What we can see is that we get back a new paragraph from WML search and replace transform, and then this code simply replaces all the nodes of the original paragraph with the nodes of our transformed paragraph. Let's go look at WML search and replace transform. The first thing that you'll see here is that it does a little check right here to see if we have any work at all to do in this paragraph. So it gets the contents of the paragraph, it finds all of the children W:(T) elements, and it gets the contents of those, concatenates them together, and then calls regex is match with those contents. There are circumstances where you could have a match right here, but not have a match down here, but that doesn't really matter. Those circumstances are really rare. It would be a circumstance where, for instance, there might be an image that is inserted in between text, and if you pass in a regular expression that would match text that spans the image, we don't want to match that text. Or there might be a tab character between two substrings of text, and the regular expression might match the text if you eliminate that tab character, but it won't match if the tab character is there. So here, this is just an optimization to see, do we need to do any work? If we don't, move on to the next paragraph. Then down here, it's going to do the very exacting search and replacement. If there was a circumstance where this call to isMatch returns true, but it shouldn't really match, that'll get caught in this code down below. It's just an optimization. The next thing that this code does is it splits all runs up into runs of a single character. This is the same approach that I took in previous versions of search and replace code, but this one has a new twist. Specifically, if you have inserted text, then this will also create separate w:\ins elements for every run that has a single character. Let me show you what I mean by that. I'm going to create a new test document for myself. I'll just call this test.docx. I'll go into the document. I am going to turn on track changes, and I am going to type in some text, hi there. Save it and close it. Let's look at this document in the OpenXML package editor power tool for Visual Studio. This is before we have split up runs. I'll format the XML. And you can see here that this text hi there is in a w:\r element, which is itself in a w:\ins element. Now let's see what that looks like after I split this text up into runs of a single character each. I'm going to modify our example here, and I'm going to want here, this is just going to be the document. I'm going to change this so we're looking for the document test.docx. I've modified the OpenXmlRegex 01 example to make it a lot simpler. I changed the selection so it selects all paragraphs in this document, and then the regex expression is hi, and it replaces that with hello. Now I'm back in the WML search and replace transform method, and I am going to set a breakpoint right here, and we're going to look at that paragraph with split runs after it gets done doing its thing. Press F5, and we hit our breakpoint. Let's look at the XML in paragraphs with split runs. I'm going to just copy all of that XML, and I'll open up a new XML document in Visual Studio so that we can look at the XML. So what we can see now is it's split up the runs in this paragraph so that there's a ins element that contains an r element that contains a t element that has a single character in it. We could save this document and it would open just fine. Word doesn't care if we did this, but we're really interested in using this form as an intermediate format so that we can do further processing. Okay, now we're back in the code where we hit the breakpoint. The next thing that this does is it gets the collection of runs of that paragraph. But one thing you'll notice is it calls this descendants trimmed method, and that's a method that I wrote for Power Tools for OpenXML. And this trimmed method, what it does is if it ever sees this w.txbx content element, it doesn't include children runs of that element. We don't want to combine looking at the runs of a paragraph with runs of an embedded text box. We want to deal with them completely separately. I'll press F10 and we get a list of runs in the paragraph. In this particular case, the runs in runs trimmed is going to be the same collection of runs as if we just called the descendants axis. This next projection here is a little bit interesting in that what it does is it looks for any run where the contents of the run are a text element. Then it returns a tuple with a character that contains that value of that text element, and it also contains the X element for the run. However, if that run doesn't contain a character, it will then probably contain something else, like either a special character, like a tab character, or that run might contain an image, or lots of other things. There's other things that can be contained in a run other than text. In the case where that run doesn't contain text, this puts a tuple in the returned collection that contains a character of 01. That 01 character, in other words the control A character, serves the purpose of breaking up that text so that the regular expression won't match text that spans an image, or it won't match text that spans a tab character, or it won't match text that spans a soft break character. When we get done with that projection, this cars and runs list will contain exactly the same number of elements in it as the runs trimmed collection. It has to. We took the runs trimmed, we run it through this projection. For every item in the runs trimmed, we projected something. Either we projected this tuple that has the character and the run, or we projected this other interesting tuple that has a character set to the control A character and also has the run element in it. This special tuple that has the control A character in it, I picked the 01, in other words the control A character, because this is a character that you are very unlikely to see in a Word document. You would have to actually artificially introduce this character into a Word document, because if you type Control A in a Word document, it selects the entire document. There are other characters I could have picked, but I picked that 01 character because it was very easy to see and easy to debug, and I felt like there's very low risk in picking that character to use as a marker for content that is not text, and we need that marker there to break up text so that the regular expression doesn't match text that spans whatever interesting content is in that run that isn't a character. And these next two lines, this is really the magic sauce of the whole thing. What we do is we take this collection of tuples and we project out each character in that collection of tuples, and then we call string concatenate, and the result of that is going to be a string in this variable content that has exactly the same number of characters in it as there are runs in that paragraph. It's just that some of those characters will be the control A character and other ones will be regular characters that we can match with the regular expression. This content string is what we can use to apply the regular expression to see if we have a match. And then the next thing that this code does is it also takes that cars and runs collection of tuples and it projects out all the runs and makes an array of runs, and I called it aligned runs. So key point here is this string content is guaranteed to have exactly the same number of characters as this aligned runs array has of items in the array. So if I press F10, F10, we can now see the contents of this string is hi there, and we can see here is this aligned runs array, and it has 9 elements in the array, and that matches up exactly to the string. We then can call regex.matches. I'll scroll down a little bit so that we can see more of this code. The code does a little bit of housekeeping, such as keeping track of how many matches we've made, because these various methods return a count of how many matches occurred. Right here it looks for if the replacement string is null, then it means we've got a match, not a replacement, and it will execute this code right here, which simply calls back into the callback method for every match. If you're not sure what that callback method is there for, take a look at the previous screencast. It explains these callbacks. Then for each match in that match collection, it first looks to see if it needs to call the callback, and if it does need to call the callback and the callback returns true, or if that callback is null, then it will do the replacement. The next thing that the code does is it creates this run collection list, and this is a query on the aligned runs array that uses skip and take, and then creates a list of the resulting collection. One thing that this does is it takes advantage of the special semantics of skip and take. Skip and take know how to deal with arrays and make the code execute very quickly. Not that I really needed to optimize this code, but I knew that using skip and take on an array is going to be very fast, so why not do it that way? The next thing the code does is it saves away the run properties for the first run. And this is because semantics of searching and replacing text in Word are such that when you replace text, the replaced text takes on the run characteristics of the first character of the matched text. So in that way, this code exactly matches the semantics of Word itself. If the first character of your matched text is red, then the inserted text that replaces whatever was matched, all of that text will be red. Now the code looks to see if we are tracking revisions or not. I'm going to look at the code that handles the case where there are no tracked revisions first, because that code's simpler, and then we'll come back here and take a look at the code that deals with introducing tracked revisions. Here, if we're not introducing tracked revisions into the markup, then it does this little bit of code here. It deletes all of the runs other than the first run. That's why there's this skip of 1. It deals with the situation where the run's parent is a w:\ins element right here. It then constructs a new first run with the run properties that we saved away previously, and with the replacement text. Now let's go back here and look at the code that deals with the case where we want to introduce tracked revisions into the document. The way this code works is a little bit different than the case where we're not introducing tracked revisions. What this code does here is it puts together the new w:\ins element that contains the appropriate author, it contains the appropriate date, and it contains the replacement string, and it adds it into the existing paragraph at the right place. It adds it before the matched text, just immediately before. So at this point in time in the code, the text is effectively in there twice. So now what we're going to do is we're going to go through every run in the run collection and do the right thing with that run based on what the markup of that run is and also based on what our author is. The first thing it does is it looks to see whether this run is in a w:\ins element, and if it is, then the next thing it looks at is whether the author of the existing revision is the same as the author passed into these various methods. And if the author is the same, then it creates a collection of the siblings of this particular run, and it replaces the nodes in the parent with this new collection of siblings. This effectively gets rid of that w:\ins that has the same author. So this handles the case where if I as an author go and insert text into a Word document, in other words the author of that revision is Eric White, and then I run this code and tell it that Eric White now wants to replace some of that text with other text, we don't need to mark that text that I'm replacing as deleted. We just need to send it into outer space. We don't need it anymore. So that's what this code here does, is it gets rid of those runs where the author is the same and we're replacing that text. In the case where the author is different, then what this code does is it creates a new INS element that contains underneath it the w:\del element, and the w:\ins element contains the same author as it always did. This code here that pulls in the attributes from the parent INS pulls in the original author of the revision that we're replacing text in. We then insert a w:\del as a child of that w:\ins, and that contains our current author, in other words, the author passed into these methods. It contains the date time of today, and it also transforms the w:\t to w:\del text elements. That's what's required when you're changing ordinary text into deleted text. So interestingly enough, this is all we have to do to implement the fairly complicated semantics that we saw in the previous screencast. If we execute this code, then that implements those semantics. This code looks significantly simpler than you might think it would be based on all of the semantics that we saw in the previous screencast. And the last thing that this code does is it coalesces all of the adjacent runs that have identical formatting, and it also coalesces all of the adjacent w:\ins elements that contain a w:\run element, and it replaces them in the case where the inserted text has the same author, the same date, and it coalesces them in the case where all of the runs have identical formatting All of that must be true in order to coalesce multiple runs of a single character into a single run. That there is the explanation of how this code works in a nutshell. There's a fair amount of other housekeeping that it does. I don't need to walk through the code that coalesces all of those runs. It's relatively straightforward LINQ code. It's very similar code to the code that you've seen in the previous version of Text Replacer. It's just a little more complicated because it has to deal with W:\ins elements in addition to W:\r elements in its coalescing activity. That's all I'm going to cover in this screencast. That's more than enough. Thanks for watching. See you next time.